Before moving any further, it's helpful if we cover some basic terminology. Now, statistics is really a language in and of itself. We'll use English words, but many of them have specific statistical meaning. So it'll be helpful if we get these meanings straight before we start talking about actual statistical content. All right, first, as a basic thing, what is a statistic? We can define a statistic as any function of data. So this could be a proportion, if we take some part divided by the whole, a sum, if we just add up the numbers, an average, a minimum, a maximum, just the count of the number of observations. These are all statistics because they are functions of data. Now, statistics are useful to represent some aspect of the data in a simple and easy to understand way. This is a major use of statistics we'll talk about, representing data in an easy to convey manner. Now, finally, statistics are defined by some operation they perform on data, like those proportions, sums, averages, and other ones we'll see in this course. So for instance, here are a number of statistics I found about what goes on the internet. Now notice that each of these statistics, for instance, that there are 2 million searches on Google every 60 seconds. Now that's a statistic. That's just the sum of the number of searches. But it's a lot easier to say there are 2 million searches than for me to show you a data set of all the different search queries and for us to have to count them up. Notice that the process of taking the sum in advance of conveying the information simply makes it easier to convey. And that's a major use of statistics, to make data easier to explain. Now we can think about two separate branches of statistics, but I want to warn you that the delineation between these two isn't as clear-cut as it's going to seem when I lay it out on a slide. But in general, we can think of statistics or uses of statistics that are descriptive, that are statistical procedures to summarize, organize, and simplify the communication of data. Now, this is a major use of statistics. When we have lots of data, we need procedures that allow us to organize and simplify the communication of the meaning behind the numbers. Many of the statistical procedures we'll learn and the visualizations we'll learn how to make are simply in the service of describing what we've observed in the world. And this is a major use of statistics. Another branch of statistics we can describe are called inferential statistics. Now, these are statistical techniques that facilitate inferences about populations from data that we collect in samples. Now, we're going to come back to the words population and samples in a minute, but if you think about just general polling, we don't poll the entire United States when we want to figure out who's going to be elected president. We take a small poll and use the sample to make an inference back to the population. So for instance, we could take the same statistic and use it in a descriptive or an inferential sense. So for example, Obama received 53.4% of the vote in the 2008 presidential election. Now that's a proportion, it's a percent. It's just the operation on data of taking the 66,882,230 votes divided by the total number of people who voted in that election. So that proportion is descriptive. It describes something that actually happened in the world. Now, the same statistic, a proportion or a percent, can be used in an inferential capacity. Notice that before the election, Obama was predicted to receive 55% of the vote in the 2008 presidential election, plus or minus 2.1%. Now, we'll come back to this 2.1% in a second, but notice that this was a Gallup poll on November the 2nd, 2008, of 2,472 voters. Now, this is not the entire electorate, and clearly we couldn't even get the entire electorate to come out to vote. But what Gallup did instead is took a sample, 2,400 people, which gave them a margin of error, something I'm sure you've heard before, of 2.1%. Now, intuitively, what we can see this margin of error to mean is simply around this 55% that we observed in the sample, the proportion of the sample that actually said they would vote for Obama. It could be about 2.1% higher or 2.1% lower than this 55% among the entire population of voters. Now, if we look at the observed statistic from the election and the prediction, it is in fact within that margin of error. Now, we'll talk more about the margin of error, but notice that the same statistic, a proportion or a percent, can be used in a descriptive sense or an inferential sense. So it's not the statistic that determines whether it's descriptive or inferential, but rather what we use it to do. Next, let's talk about the word data. Now, data are measurements or observations we make. The word data is plural, and so you say data are collected rather than data is collected. Now, a data set is something you'll also hear me say, and that's the collection of measurements or observations. And if you really want to refer to a single data point and don't want to say the word data point, you can call it a datum, which is the singular, and that's a single measurement or observation. We'll also call this a score, a raw score, or a data point. Next, let's talk about the word population, and this is an important one. A population is the set of all individuals or units that we're interested in. Now, this could be anything: plankton in the ocean, people in the world, people at UCSD, dogs in San Diego. These are all populations if that's the thing we're interested in studying. Notice then that a population is somewhat of a subjective choice. What you intend to make inferences about is the population you are concerned with. So, the size of the population could be as small as a classroom, if that is the set of individuals you actually care about characterizing. Or the population could be infinite, if you would like to try to describe all humans who will or have ever existed, which in essence is the purpose of cognitive psychology or neuroscience. It turns out that the size of the population isn't really of material concern, and we'll come back to why that is. For now, though, know that the population is the thing we want to make inferences about, but it's usually something that we can't observe, either because it's too large or because it would be too costly to take measurements from every individual. So instead, we take a sample. A sample is a set of individuals or units that is selected from a population. Now, we take a sample because we use it to represent the population in lieu of actually measuring the entire population. Now, to make a representative sample, we'll often refer to something called simple random sampling, which is simply taking individuals at random from a population. Now notice that this will return a more or less representative sample, better than systematic sampling often. If we are taking individuals from the population systematically, for instance, let's say I'm interested in the heights of all students at UCSD, but I systematically sample only the tall individuals, clearly that won't be a representative sample. However, if I take random individuals I pass and measure their heights, I'll more or less get a sample that happens to contain the types of people who are in the population. We'll come back to the idea of simple random sampling, but this is often an assumption we make when we're taking our samples. Now, samples are usually much smaller than the population, which of course is the reason why we take a sample in the first place. We need the sample to be small enough so that we can measure or work with them, since the populations we care about are usually too large. Now, when we actually get into doing science and doing research, we're going to quantify characteristics of our samples. And remember, our samples are useful to represent or stand in for the population. But anything we calculate on our sample will not necessarily be exactly the same as if we had calculated it on the population. So this leads us to a very important distinction that may seem pedantic right now, but is in fact a very important thing to remember about our entire statistical process. And this is the distinction between a parameter of a population and a statistic of a sample. Let me step back. Remember, the population is the thing we actually care about quantifying, and the sample, usually much smaller, is the thing that we're actually working with to make the inference to the population. Now, populations and samples can have the same types of measures: averages, sums, maximum scores. These are all statistics in the sense that they are operations on data. But when we have an average of a population, or a sum or a maximum score in the population, we will call those values parameters. And the same values, when we calculate them in samples, we'll simply call a statistic. This distinction is critically important. Parameters describe something true in the world. The average height of all individuals in the world is a true value. If I take a sample of all individuals in the world, even a simple random sample, the average I calculate for my sample, which remember I'm trying to use to make an inference to the population, that average in the sample won't be a perfect representation of the population average. So we wouldn't want to call a sample average a parameter. It could be wrong. And in the sense of wrong, I mean it could be different from the population. So a parameter is a value, and usually numeric, that describes the population, whereas a statistic is a value that describes a sample. And remember, we're using statistics to make inferences to parameters.